Okay, welcome to this 10th lecture on electrical machines 1, and we were trying to get a realistic model of a practical transformer. Ideal transformer is real ideal, where no winding resistance, no core loss, no leakage flux, and things are very simple, and I know how to calculate secondary current, primary current, draw the equivalent circuit, so on. Then what I started telling you that to an ideal transformer, if we go on adding some parameters, some elements properly, then that will be the model of a practical transformer. We are trying to model a practical transformer in terms of model of a practical transformer. I am trying to get by an ideal transformer plus some circuit elements. We are adding circuit elements, and I told you that till now what we have done is we have added the winding resistance R 1 of the primary, and this is my ideal transformer. And here is your actual load on the secondary side Z 2, and here also I showed the secondary resistance R 2, and then the magnetizing current was also taken into account, and it was not a winding, it is JXM. It is my thought process which brought me here. This is my applied voltage, and these are the current. When it is closed, it is I 2, remember this is I 2 dashed, and this is I m, magnetizing current, which is very small, x m is high. Mind you, I write it here, x m high, R 1, R 2 are small. That is why people do while analyzing, suppose a circuit is given, practical transformer. Okay, apply the rules of ideal transformer. Suppose you do not have any parameter values known, x m, R 1, R 2. You for example, if I say it is useful to know, so that suppose the same transformers, one transformer is rated like this, 200 volt, 100 volt, 1 kVA, 50 hertz transformer is given single phase. Suppose I say that it is suppose a practical transformer. Okay, you apply 200 volt here, you and I say you connect an impedance, say 10 ohm, practical transformer it is. But what I am telling, suppose you want to quickly calculate, assume this transformer to be ideal, because after all these R 1, R 2 are small, x m is high, and then calculate the currents. This side 100 volt, 10 ohm, 10 ampere, sorry, this current is 10 ampere, and say that this current is 5 ampere, and this voltage is close to 100 volt if you have applied 200 volt here. If you have applied 200 volt here, 100 volt. So, while estimating, okay, this is a practical transformer suppose, but for quick calculations you do this, and to this practical transformer you really connect a 10 ohm and 200 volt. What I am telling is, you will not be very far away from this 10 ampere, this 5 ampere, it will be very close to that. So, the concept of ideal transformers in many ways help me, or very complicated circuit, so many transformers, each one will have R 1, R 2, X M 1, X M 2, but I know X M is high, R 1, R 2 are small, neglect them. For getting a quick idea what will be the order of the current, what will be the order of the voltage across the load. It may be in a practical transformer instead of 100 volt, if you have applied 200 volt because of this drop, it may be 96 volt, but who cares. So, but you get the ideal transformer helps you to calculate the number so easily, and you can always say it is very close to the correct answer. It is not a mean achievement using the concept of ideal transformer, wherever possible you do that. So, that is there, but still now let us see whether those parameter values can be taken into account. If it can be taken, how? And to do this, I told you this portion is ideal transformer, and go on adding parameters, do it like this. Achha, next thing is, I have assumed in the transformer that all the fluxes are leakage flux. For example, consider the core of the transformer. Suppose you have a transformer, this is the thing, and what I have assumed earlier is that here is your some winding, and I assumed that all fluxes were confined to the core. In reality, in a practical transformer, it is not going to be like this. There will be flux lines, most of the flux lines will be confined to the core, because it will be highly permeable material. So, most of the lines of forces will be confined, maybe 2%, 3%, 4% flux line will complete their path through the air gap. Therefore, when the conductor carries some current, it produces flux, a little amount of flux will be leakage flux. So, this is called the mutual flux, this is called the leakage flux. It is this mutual flux which is going to give you transformer action, is not d phi m dt, d phi m this is the voltage induced in the coil is d phi m dt, no leakage flux. The flux which is common to both the windings. So, this is leakage flux here phi L 1. Therefore, the induced voltage in the coil of the transformer will be d dt of phi m plus phi L 1, is not, into N 1 say. This is the induced voltage in the coil, and this can be separated out, d phi m dt plus N 1 d phi L 1 dt. Now, this portion, this term is not going to transfer energy from the primary to the secondary side. It will simply cause a voltage drop. And it can be written as LL1 d IL1 dt. I mean something like that primary current whatever is flowing, leakage flux. A detailed analysis I have done it in my machine 2 course in the first few lectures. Electrical machine 2 course in the first 2, 3, 4 lectures in the same NPTEL domain. If you please go through that, it will I will put a note on that, but it looks like the applied voltage total flux created by the winding currents will comprise of two portions. One is the mutual flux, which will be totally on the core, another is the leakage flux. This leakage flux will complete their magnetic path through the primarily through the iron. Their reluctance is high, leakage flux itself will be small, but nonetheless it will cause an extra voltage drop. Therefore, it looks like applied voltage I have given, there will be a voltage drop in R 1, but there is a small inductance drop which will also take place to take care of this voltage here. In other words, what I am telling, out of this total applied voltage, a portion will be dropped in the small resistance R 1, and also there should be a small inductance drop taking place, and the remaining voltage is as if going to the ideal transformer, giving you mutual flux alone. So, it looks like it should be like this then. Let me first draw. So, leakage flux, the term I have written leakage flux, you write it, leakage flux causes an extra voltage drop, small voltage drop in the coil, in the practical coil. What does that mean? It means that if first I draw the ideal transformer N 1, N 2, and this portion is suppose ideal transformer, it is no connection, dotted line, okay. And then we have seen you have got R 1. Now, what I am telling, in series with R 1 there must be another small inductance X L 1, and then this is your J X M, and then this is your ideal transformer, this is your E 1 and this is your E 2. In the secondary side too, it will carry current, it will produce flux, a portion of it may be leakage flux, and therefore, winding resistance as well as leakage reactance X L 2, and then these two are the terminals, and here is the secondary impedance you have connected. Therefore, this and this is the ideal transformer, here all the fluxes are mutual, mind you, all the flux here it is phi m mutual flux plus phi L 1 N 1 phi L 1 d phi L 1 dt is shown as a drop here, because this is your supply voltage. Now, we know out of this total supply voltage a portion will be dropped in R 1, absolutely no doubt, and there will be another small voltage drop because of leakage flux, which is not going to create your magnetizing current. No, that voltage is consumed by the leakage flux. As in any inductance, you know, inductance. Whatever is the flux, that is the drop here, and it is not mutually coupling to another coil. Therefore, no energy transfer because of X L 1 from primary to secondary side. In the same way as in the primary, secondary side too then will have winding resistance, another. I have used very small letters x to indicate leakage flux also will be small in a well designed transformer. Who wants more voltage drop takes place elsewhere and less voltage is available for transformer action. It is this voltage E 1 which is nothing but the applied voltage minus this drop must appear here. If X L 1 is high, once again it is a very bad transformer. Out of this total voltage, transformer winding impedance consumes so much and little voltage, less voltage is available for energy transfer. Therefore, remember that this is the situation now. So, leakage flux, effect of leakage flux can be taken care of. Once again, leakage flux I should not draw it here, no, because applied voltage that will be only consumed in the winding, and it must be in series with the supply lines JXM, this one. And once we do that, I will repeat this once again, that I do not know whether I have gone it a bit faster without defining what is leakage inductance and magnetizing inductance. But I request you, please go through the first few lectures of electrical machine 2 course, which is already uploaded in NPTEL website. You will get a better feeling of this one. Nonetheless, so this is more or less the all the parameters we have added to an ideal transformer to represent a practical transformer. This is the ideal part, add these two things and pretend that this is the model of the practical transformer. Only one thing I have yet to take, that is called the core losses, that I will discuss, but so far as this one, core loss not yet taken into account, not yet. Core loss to be taken into account, to be effect of core loss to be taken into account. That will do, but before that the addition of this one, mind you, I write it, emphasize this point, these are small numbers, this is high number. High with respect to whom? With respect to these numbers, quite high. Similarly, these are small. Okay. Now, in this case, once again let me do that, because suppose S 2 is closed, what will be the thing? There will be some current I 2 here. The moment through the secondary of the ideal transformer I 2 flows, through the primary of the ideal transformer I 2 dash 2 will flow, and this current is I m and this current is I 1, that is what is going to happen. How to draw the phasor diagram? Okay, suppose the power factor is same way, suppose I will sketch once. So, let us start. So, suppose you draw first, let us assume this is LV side. Okay. So, V 2 is first sketch, V 2. I know load power factor angle, I will sketch I 2. let me draw it larger, because low voltage side current is higher. Suppose this is I 2. All are phasors, I am not putting those words. I 2. Okay. So, V 2 is there, but V 2 and E 2 are not same. In between comes a small impedance. So, what will be E 2? E 2 then will be equal to V 2 plus I 2 into R 2 plus J X L 2, is not? The drops here are like this. This is plus minus. So, V 2 to this at these drops get E 2 plus minus. This dot I have put. So, V 2 plus I 2 R 2 parallel to this, and plus J I 2 X L 2, and if you add this you will get E 1 E 2. If you get E 2, then your E 1 in phase with E 2. So, your E 1, I will draw a different color. So, your E 1, I will fix up, suppose this is your E 1. Once I get E 1, I will say, oh, my magnetizing current is this voltage by this J X M. So, I will draw a magnetizing current, which is 90 degree lagging E 1. And if this is I m, your I 1 will be I m plus I 2. So, add this I m, I 2 dashed, I am so sorry. So, I 2 is this one. So, I 2 dashed will be less. So, I 2 dashed, correct. So, suppose this is I 2 dashed. So, it will be like this, then this was I 2, mind you, this was I 2. So, from I 2 you get I 2 dashed, then I 2 dashed plus I m, you add I 2 dashed plus I m parallel to this I m, and if you do, you will get I 1, and if you get I 1, then E 1 to E 1, if you add these two drops I 1 into R 1 plus J X L 1, small l indicates leakage reactance drop, and this must be your V 1. My target is to show all the variables. So, E 1 I have reached. So, to this E 1 you now add I 1 R 1, E 1, add I 1 R 1 parallel to this, wherever it is I 1 R 1, and to this you add I 1, which is 90 degree, I 1 J I 1 X L 1, and get your supply voltage V 1. This will be the, and here is the flux along this line. I think you have got the idea. It looks like, oh, it is quite involved. No, not really. We will see later how things will become much more easier. With few approximations here and there, things can be further simplified. So, what I told you that it is almost a practical transformer, except core loss is yet to be taken into account, where I have considered the winding resistances R 1 R 2, where I have considered the finite magnetizing current, and the effects of this are easily seen. See, I can make one comment. So far, I was telling that the moment you apply a certain voltage at a certain frequency, the flux level in the core is decided and that is constant. But when the transformer will be operating, when the windings are carrying current, applied voltage is not creating flux. Flux is created by this voltage, and this voltage E 1 is V 1 minus this drop. But the thing is R 1 X L 1 is small. So, E 1 and V 1 I can say magnitude of V 1 will be not exactly equal, but their magnitudes will be very close by. Because of what? Because these elements are dropped. Similarly, E 2 and V 2 will be also very close by. Because R 2 X L 2 are small. Therefore, we can say roughly that the flux level even in a practical transformer, it will change as you change the value of I 2 by varying Z 2 I 2 will change. So, this drop now with another value of Z 2 it will be different. Similarly, here I 2 dash will come I 2 dash plus I m and so on. So, these drops are small for a well designed transformer. Therefore, it is not very incorrect to say that flux level does change appreciably from no load to full load condition. The change in flux level is pretty small, because R 1 X L 1 and R 2 X L 2 are small. Anyway, in the next class what we will do is this, we will tell you about the core loss, which is very important. Core loss, we will see that it comprises of two components. One is eddy current loss, another is hysteresis loss, and when a practical transformer is operated, if you touch the core, you will find core is becoming hot. Okay? Although there is no electrical connection between the conductors and the core. So, that is another interesting topics that we will take up in my next class. Thank you.